Hi everyone, and welcome to Module 1 of Course 3. In this course, we are going to discuss a variety of advanced methods that can be used when looking at data sets. This process is sometimes called data mining. In the first module, we will discuss some common definitions and features of healthcare data. At the end of the module, you should have a good understanding of some of the complexity that comes with analyzing and interpreting large databases. The place that we need to start with is a good definition of what data mining actually means. Understanding the definition will help you get your head around the specifics of what the rest of this course will be about. It will also help you explain to others why data mining can be helpful in many situations. Data mining can be thought of as statistical modeling, finding patterns of data, or even knowledge discovery. A technical definition of data mining is that data mining is a business process for exploring large amounts of data in order to discover meaningful patterns and rules. It can result in new and interesting ideas that lead to new directions of exploration, which in turn leads to more data analysis. If we break down each section of the definition, we can get a better understanding of how this idea can help in day-to-day information requests. First, data mining is a business process, or should be thought of in that way. It interacts with other ongoing processes and doesn't necessarily have a beginning or an end. Data mining can be helpful in achieving many business goals, such as a better understanding of your customers, planning for staffing, or understanding market research. Second, data mining is generally used when you are dealing with very large sets of data. These large sets of data often have multiple attributes and can occur in multiple formats. In healthcare, this is a common situation, particularly when you are investigating questions at the state or national levels. A key in data mining is understanding how to tell the computer to find the subset of information that you are looking for, and how to use the amount of data to your advantage. Finally, the end goal of data mining is to use these business processes and large amounts of data to provide meaningful patterns. One thing to remember here is that it is generally fairly easy to find patterns. The trick is finding those that can tell you something about the set of data that will be useful to the business. This is all well and good, but why is this important? In short, data mining will allow you to make use of the vast amounts of data that is collected on a daily basis. This means that you can use your data mining skills to gain a better understanding of both the local situation as well as the larger picture. How is data exploration different than documentation? They seem rather similar at first glance, but the biggest difference is that documentation just tells you what data should have available. It doesn't tell you anything about the data or what's missing. Data exploration, on the other hand, can tell you exactly what is there and what's missing. It can also tell you if something unexpected shows up, or if the data expected is in the wrong format. It can tell you if there are relationships between columns and what those relationships are like. It can tell you how often a specific piece of data occurs in the column, or even in the data set as a whole. What most people do with data is document the data. It may be a slight rearrangement of the data into a table or chart, but essentially they are just looking at the data that should be there. What this module starts diving into is the process of exploring or mining the data. There are many more things the data can tell you than you ever think it could. The issue is just knowing how to get at those things. Most of you, at some point in your life, have seen the children's television show, perhaps even Sesame Street, which looks at the concept of same or different. This is one of the key pieces of data mining, knowing how to tell if something is the same or different than others in that column, row, or data set. To set yourself up for success, you need to take a look at the type of data you are working with and know the characteristics of that data before you can answer the question, same or different. As just discussed, one of the greatest assets of good data mining is to help define relationships between data. We want to know if one set of data is similar or different when compared to another. Once we know what our data looks like, we can start doing things like determining clustering of data points, classification, or determination if anomalies exist in the data. From all our past discussions around data, you should know that a set of data is usually seen as a collection of data points or objects. Other terms you might hear for a data object might be record, event, case, sample, observation, point, pattern, or entity. Some of these terms are more commonly seen in healthcare than others. In order to describe these data objects, you need to know what attributes the data may have. You need to be able to understand the basic characteristics of the data you are looking at in order to understand how to handle it. In addition to being known as characteristics, attributes can also be called variables, fields, features, or dimensions. Let's look at a quick example before we go any further. On this slide, you can see a sample set of data that contains information about a few patients served by a local healthcare facility. Each row corresponds to a patient, and each column contains some aspect that can describe that patient, such as the patient ID, birth date, or blood pressure. So what can we do with these attributes? First, you need to know that an attribute is a property of the data object and can vary in some manner. In our example, blood pressure is an attribute of the patient, and it can vary from visit to visit. It will also vary between patients. If it didn't, that should raise a red flag that more investigation needs to be done. In order to work with attributes, we need to think of them as being on a measurement scale. Not all attributes will be numeric in nature, but it is generally easier to think of them in numeric terms. Thus, we can then think of a measurement scale as a set of rules that associate a symbolic value with an attribute in order to allow for comparisons. For example, two attributes associated with our patients are patient ID and birth date. For patient 5, it would really make no sense to try and find an average ID number, but you could look at all patients whose ID number starts with 4 or 5. What we are measuring in the attribute of patient ID is that they are different. We could find an average age of our patients and use that to make comparisons with. Why do we need to know the attributes of our data? We need to know the type of attributes so that we can make comparisons. Recall, we discussed some of these concepts in Course 1. Common comparisons are distinctness, or are the data objects equal or unequal? Order, does one data object come before or after another, or is it occurring at the same time? Addition and multiplication, which are standard arithmetic operators. In addition to these commonly used attribute types, we have another set of less well known. These are nominal, ordinal, interval, and ratio. Looking at the previous list, you should be able to see some connections. A nominal attribute is a value that is just a different name for the same type of thing. For example, zip codes, eye color, gender, and patient ID are all nominal types of data. There is just enough information in the attribute to distinguish one thing from another. An ordinal attribute has enough information for us to put the data objects in a particular order. Ordinal attributes can be such things as clothing size or order of finish in a race. An interval attribute is an attribute where the difference between values are meaningful, as a measurement system already exists. This might be dates on a calendar, blood pressure readings, or temperature in Fahrenheit versus Celsius. Finally, a ratio attribute is an attribute where both the differences between variables and the ratio are meaningful. These attributes are things like count, age, mass, length, monetary units, and electrical currents. Interval and ratio attributes can be thought of as quantitative or numeric in nature. Additionally, attributes may either be discrete, meaning having a finite set of values, or continuous, having values that can be floating. Some examples of discrete attributes would be zip codes, ID numbers, or even counts. Continuous attribute examples would be height, weight, or temperature. In actuality, we can only measure continuous attributes to a certain amount of precision. One last type of attribute is an asymmetrical attribute. This is a situation where the only thing we care about is if it is either present or not. For example, let's say we're looking at patients' records and we are interested in diagnosis codes. We have one record for each patient, but our patient will probably not have all of the diagnosis codes. If the patient did not have a particular diagnosis, the attribute in the patient record is recorded as a yes or a 1. If the attribute is not present, it would be recorded as a no or a 0. Now that you know the different attributes that individual pieces of data can have, let's talk about types of data sets. First, we'll talk about some general characteristics of most data sets, and then we'll go into more specific characteristics. The basic characteristics of most data sets include dimensionality, sparsity, and resolution. The dimensionality of a data set is the number of attributes the objects in the data set possess. If we go back to our patient record example, the dimensionality of a specific patient's record is the number of different columns or attributes it might have. At first thoughts, data having lots of attributes or being highly dimensional sounds like a good thing, because you can look at all sorts of relationships, right? As you think about it more, you may come to realize that in some instances, too many attributes may actually cause issues in analyzing data. The next general characteristic of a data set is sparsity. Sparsity has to do with a situation when a data set is asymmetrical. If you remember our definition from the last slide, you can probably guess that asymmetrical data is rather sparse, meaning that the values of most attributes is 0. This can be a benefit if you only need to store the non-zero values. Third is resolution. Resolution is looking at the data with different levels of detail. For example, it may not make sense to measure the time between patients' visits in minutes. The resolution is too detailed and the patterns in the data set will be lost. Resolution can also go the other way. If the resolution is too small, we are measuring the patient's visit in decades, we can still lose our possible patterns. Now that we've covered some general data set characteristics, let's take a look at some of the types of data sets you might come across. The first is record data. Record data is exactly what you think it is, a data file that has a fixed set of data fields or attributes. Two common examples of record data are transaction data and a data matrix. Transaction data is a set of records in which each record involves a set of items. For example, think of a pharmacy. The prescriptions given to a patient are a transaction, and the specific drug making up that prescription are the items. A data matrix is similar to transaction data in that it is a set of records, but in a data matrix, all the items are numeric in nature. Graph-based data sets are what most likely come to mind when you read the term. They are data sets that use graphs to show either a relationship in the data among the different attributes, or a set of data in which the data objects themselves are graphs. An example of the first situation is a web page. Most web pages contain both text and links to other pages. An example of the second situation is the common drawing of a molecule used in chemistry classes. Dots for electrons and branches showing links in different parts of the molecule. An ordered data set can be thought of in one of three ways: sequential, a time series, or spatial. Sequential data sets are often used to determine when something occurred. They can be paired with transactional data sets to determine things like prescription history of a patient or what time of year certain procedures may tend to occur. Sequence data is similar, but has no time associated with it. It only has positions in an order. The best example of this is genetic information. We know changes in the sequence of DNA can cause different things to occur. You might be wondering at this point what the difference between sequential and time series data. Time series data is a series of measurements taken over time. For example, the average monthly temperature in Lincoln, Nebraska during the years 2002 to 2005. Spatial data is a data type that is often used in science and engineering disciplines. It is data that has spatial attributes such as positions or areas. One example of spatial data is weather data that is recorded for different geographical locations. Let's introduce some terms that you'll come across as we move through this course. A data warehouse is a location in which all data are stored. The data warehouse contains all of the data that is gathered by different input locations and contains it in one location. You may also have regional and state level data warehouses. Once the data are gathered and housed in a data warehouse, it is then accessed through different database systems known as data marts. A data mart is a data store or database that is similar to a warehouse but is limited to a single subject grouping. In addition to learning where and how data are stored and how to access the data in different ways, this course will also help you to understand a few different methods of analysis: survival and historical. Survival analysis is looking at which customers or patients are retained in a system. Ideally, we want our customers and patients to return for multiple visits. Performing a survival analysis on our data can help us understand why we might be losing customers, or why patients are not returning for additional care. Historical analysis is generally what it says. It looks at the past to help us understand the future. In other words, in historical analysis, we are looking at what already has been done and using the information to tell us where we are and possibly where we need to be. This is the type of analysis most of you are probably familiar with and may have even performed in the past. The last thing we are going to discuss is the customer signature or customer analytical record, CAR for short. It is a data structure that ties everything back to a specific customer, or in healthcare, a specific patient. This can be done by creating a record based on the patient's social security number. All encounters, visits, procedures, prescriptions, or any other activities relating to a patient are all connected, regardless of where they occur, by patient ID or social security number. In a perfect world, you would be able to take data from any one of a number of data marts and tie the data together based on the CAR. In reality, not all of the data will match up nicely, and you will have to use your data mining skill set to combine data from different locations into manageable, useful information. The first step in understanding how data mining can be used and how it can be useful is to understand the structure of a database. Most databases, warehouses, or data marts are one of two types, either transactional or subject-oriented. A transactional database is designed to help process individual transactions as efficiently as possible. They mainly handle operational requests. A subject-oriented database is designed to assist in decision-making. These types of databases are usually set up to handle analyzing and reporting of data on a specific topic, such as data about heart disease. Most of the data you will be using during a data mining process is stored in a transactional database. This type of database structures pieces of data as separate entities with different types of relationships tying them together. An entity can be thought of as a group or a class of data. When defining a group, you need to also define its attributes to distinguish it from other groups. Each entity can have more than one attribute. For example, an entity may be a specific cohort of patients defining those who are male and have heart disease. Each entity can then be tied together through relationships. Relationships can have three types: one-to-one, one-to-many, and many-to-many. A one-to-one relationship can be thought of as similar to that of husband and wife. An example of a one-to-many relationship would be a mother to her children. A mother may have more than one child, but each child only has one biological mother. A many-to-many relationship is that of a college student to a professor. Each professor has many students in a class, and each student has more than one professor. Finally, the usefulness of transactional databases come from its ability to use those relationships to help you mine the data or patterns in relationships. Often, many of these relationships are given identities in the system. They may be assigned a number, such as a diagnosis code, a patient's social security number, or a provider's location code. The identities may also be text-based, such as providers' names, procedures' names, or locations' names. Just because you know how and where certain types of data are stored and how to access those records doesn't mean that you can always use what you know. As a business, you have customers. Knowing who your customers are, what services they are likely to need, and what they think of those services when delivered are all important to providing the highest quality care you can. So, back to our question, who is the customer? Depending on where you are located, and possibly the project you are working on, your customer could be a patient, another department, or an entire facility. Once you have a sense of who your customer is, you can begin to learn about that customer in order to help your data mining and subsequent analysis. One of the pieces of information you need to know is how are customers described and located in your data warehouse. The most common ways are in a physical data mart, a virtual data mart, or in a householding system. A physical data mart would be the situation where a lookup table or fact table pulls information about the customer from a variety of different data sources and pulls them into an easily searchable but limited format. A physical data mart is limited to the pieces of data in the table. If you want to find something that was not in the table, you would have to find another way to obtain the piece of information. A virtual data mart allows you to drill down to specifics about a customer, whether or not that piece of information is located in the table you are using or not. A virtual data mart talks to the data sources, allowing you to direct queries based on what you are finding. The third type of system is a householding database. A householding database is able to pull together all similar records, so if a patient's name is one letter off but has the same phone number, a householding system would list those records as a match. Once you understand who your customer is and where you might be able to find the information to need, you can start to build a customer record. You've determined who your customer is, you've got some data that you hope will be useful in answering your project's question. Now what? You need to organize your data into a format that is easy to search and manipulate. This may be a pyramid report or an Excel spreadsheet. Depending on what you're working on, it may even be a set of Post-its on a wall. The goal of your organizational process is to create a customer record. A customer record consists of a single record per customer. This may mean that you need to consolidate multiple rows of data into a single row. Maybe you will need to transfer information from multiple patient visits into a single record. The main reason that you want one record per customer is so that you are able to easily mine the data and not miss something. Once you have your data organized into a single record for each customer, you then want to start determining what attributes or variables will be useful for you in your analysis, and which will not. Before you start removing attributes, make sure you save the original data set. I usually make a copy of my original data set so that anytime I can refer back to the original. In addition, somehow make yourself a note giving the step-by-step process you use to obtain the data, what data cubes, time frame, dates, etc. This will make it much easier for you to repeat the data pool at a future date if you need to pull the data again for some reason. Once you have your original data stored in a safe place, you can then start removing data attributes that are not helpful. For example, if you are interested in looking at diagnosis by location, knowing a patient's age or number of visits may not be hugely relevant, so you can remove those columns. For some people, rather than removing the columns completely, it is easier to use the hide columns function in Excel. This way, the data in those columns can be brought back at any time and is sorted with any data sorts you do. Again, you want to document your work. Somewhere, keep track of what you have done to the data. If you remove or hide columns, make a note. If you sort the data, make a note, particularly if you do multiple sorts. This will save you all sorts of headaches later on when you're trying to either repeat your data manipulation or trying to explain it to someone else. Now that you have your data organized and document your steps of organization, you can start to assess your attributes and really dig into the process of finding a pattern. One thing you want to keep in the back of your mind whenever you're doing a data query, creating a report, or performing an analysis is that data mining allows us to look at the past and learn from it. It allows us to use information that is already available to enable better decision making in a variety of ways. That being said, however, there are still some pitfalls that you want to avoid when mining your data. You don't want to start seeing things that aren't there, and you don't want to be able to find what you are looking for. One of the biggest pitfalls that you need to be aware of as you do data mining and data analysis is that you always need to verify what you found. Finding or learning things that aren't true can be more of a hazard than finding out something that is useless. This is because often decisions will be based off the data you've collected or the analysis you've done, and that decision can only be as accurate as the information that you provide. Just because the results seem reliable doesn't mean they are reliable. It is up to you as the data analyst to verify your results. A common misunderstanding often occurs with patterns. If you look at any set of data long enough, you can find a pattern in it somewhere. That doesn't mean the pattern is useful or even usable. Some patterns are useful, such as the changing of the season. This pattern can be used to predict certain occurrences, such as which facilities may start seeing snowbird patients in November. Some patterns aren't useful. For example, when the Washington Redskins win their last home game, the incumbent party keeps the presidency. How well a football team does has nothing to do with predicting who wins the presidency. However, we still like to look at patterns to give us an idea of what might happen. To decide whether a pattern is stable and useful, you need to compare it to multiple random samples. These samples should be taken from the same population. This makes sense. You want to have your samples be as similar as possible. But how do you know if your population is the right population? Remember, we said in Course 1 that your analysis can only be as good as your data. And this means you need to make sure you are choosing a population of data that reflects what you are trying to model or predict. Also, as you learn in Course 1, any sample that doesn't reflect the overall population being studied can be considered to be biased. When you're putting together the population or data set you are interested in learning more about, you also need to pay attention to the level of detail. The issue of level of detail is something that you should always be prepared to explain to anyone reviewing your analysis or results. One of the biggest pitfalls that you need to be aware of as you do data mining and data analysis is that you always need to verify what you found. Finding or learning things that aren't true can be more of a hazard than finding out something that is useless. This is because often decisions will be based off the data you've collected or the analysis you've done, and that decision can only be as accurate as the information that you provide. Just because the results seem reliable doesn't mean they are reliable. It is up to you as the data analyst to verify your results. The goal of data mining is to provide new information and insight into past occurrences. This can sometimes mean finding patterns that are already known or should be known. For example, a strong pattern in healthcare is that usage of health services increases with those patients who are older. This makes sense, as the older a person gets, the more complex their health situation tends to become. In another example, if a northern clinic only looked at its usage data in the month for a single fiscal year, it might notice that its services are utilized less in November and December. This could lead to the conclusion that something happened at that location that year to drive patients away. Since you have all been through the first two courses, you should be thinking, oh, wait a minute, what does the year-to-year comparison look like? Is this happening every year at the same time? Without asking those questions and without comparing itself over a multi-year period or to clinics of a similar size, the Northern Clinic will come to an inaccurate conclusion. We know that oftentimes clinics in the north experience the flight of the snowbird population to warmer areas, typically in the south. If there are clinics in the southern part of the country that see an uptick in usage during the winter months, and if this is an annual occurrence, the Northern Clinic can adjust its thinking appropriately and not panic. A positive with finding out what you already know is that you are able to confirm what your choice of data mining techniques and analysis is working well, and your data seems to be reasonably accurate. Not always helpful, but reassuring nonetheless. In addition to finding out things that are already known, sometimes data mining finds things that, although they are interesting, can't be used. For example, in the Dakotas, it is known that there will be a winter snowstorm or blizzard, generally at least once a year, that requires the closure of roads. Reviewing the usage of services during the winter, you will probably find that there is a lower clinic usage during the winter months. This doesn't mean, however, that we can completely close the clinics and hospitals in the Dakotas for those months because there may be a blizzard. Another medical example that continues to make headlines is the issue of genetic predisposition to particular diseases. This is information that data mining discovered. However, it cannot be used by insurance companies to deny a claim or coverage. As a quick review, let's take a look at the steps of the scientific method. Most of you probably learned about this back in elementary or middle school. As a refresher, the scientific method starts by defining the project you want to work on. Once you know what you are trying to work on, you can start to gather the initial existing information and use this to create your hypothesis. Once you have your hypothesis, you create and run an experiment to test your ideas. You then analyze and interpret the results and use these results to help you draw a conclusion. Remember, when coming to a conclusion, most of the time you use existing data, the results from your new data, and your own experiences to help you determine what the conclusion is. Based on this step, you may again create a new hypothesis that points in a new direction, and off you go again to step 4. This is pretty straightforward, and you're probably thinking, why are we reviewing it now? We are reviewing the steps of the scientific method because the process of data mining is very similar. The biggest difference between the classic scientific method and the process of data mining is the classic method relies mainly on deductive reasoning, steps 1 through 5. And data mining relies on inductive reasoning, steps 6 through 9. Inductive reasoning is the idea that part of the way in which you reach your conclusion is to not only use the data to help you make your decision, but also use heuristics or your background, experience, and gut feeling to help you arrive at your final thoughts. Now that we've reviewed the scientific method, let's take a look at a process for data mining. As we walk through this process, you should be able to see how it relates to the scientific method. Depending on the reference, the data mining process generally contains between 4 and 7 steps. In our case, we're going to use a 6-step process due to the complexity of the information that is available to you. The first step is to specify the need. The main objective of this first step is to clearly define what you're trying to achieve with your data mining project. What questions are you trying to answer? What is the level of urgency? Meaning, are you looking to create a one-time report or set up a briefing book that can be updated on a regular basis? Also, this can mean how soon does it need to be completed. You also need to define the time frame for your data. On the last slides, we talked about some of the major pitfalls in data mining, one of which was understanding the time frame you are working with and how that will affect your results. You need to know what elements of data you are looking to work with. Do you need location, unique patients, or only departments or diagnosis? And along with this, you will need to know what levels of measurement or detail is needed to answer the question. The better you can define these items up front, the more focused your data mining will be. The second step in the process is to locate the data elements. This step can often be the most time-consuming. This is because there are often several data cubes or reports that contain the same or similar information. The key here is to find the cube or cubes that give you the best data. When you are looking for your data elements, make sure to check more than one location. This is important as different cubes or reports will be updated at different frequencies. You may have 2 sources that show similar data, but if one is only updated on the 15th of the month and one on the 15th and the 30th of the month, your data will be off if you pull the data on the 3rd of the month. The easiest place to find the frequency with which a source is updated is to read through the data definition file. Until you are able to write a code called SQL, you will need to rely on previously created data cubes as your main source material. Step 3 is to generate information. There are a few substeps to this that you should already be familiar with. Once you've downloaded your data, you will need to clean and organize it. Once this is done, you can use tools such as Pyramid and Excel to help you create information from your data. Step 4 in the process is to evaluate the information. You will need to look at your data to make certain that you have the correct data elements and that it will fit the required time frame. Something to be aware of as you are working through steps 3 and 4 is that different database systems process the data slightly differently. Some may only use the diagnosis code, some may use the code in the name, others may only use the name. In the same vein, some data sets will leave a blank cell for missing pieces of data, others may put in a 0, and yet others will remove the piece of data altogether. You will need to review your data in order to validate what you have found. Run some samples through your pattern to see if they are successful. Test your ideas to make sure that your data can support them. Step 5 is to analyze the report. Once you have your data cleaned, organized, evaluated, and validated, it is time to create a report of what you have found. This report will most often be in Excel, but could also be in Pyramid depending on what it is designed for. As the one who did the data mining analysis, you need to make sure that you understand what you are seeing and are able to articulate why you see what you do. As you've learned in past courses, you need to be able to back up what you are showing. In addition, you also need to be able to spell out any limitations that your analysis has. These may be things like time frame, location, or available services. Again, you need to be able to tell your audience what exactly this analysis can and cannot be used to predict. Once you feel confident in step 5, you can move on to step 6, turn information into knowledge. This may be issuing the report or recommending a process change. It may be providing financial data to allow for changes in budgeting practices. It could lead into changes in marketing or in almost any aspect of doing business. Without an understanding of how you can apply your results, you don't have knowledge. You only have information. During the next few weeks, we're going to try and walk through the different methods of analysis that might be useful in the data mining process in order to give you an understanding of how you can conduct a data mining project of your own. Each week, we'll give you a detailed look at how you can use the vast amounts of data available to you, your benefit, and how you can apply these tools to your daily job tasks.